Okay, so welcome to section 8.1, which is apportionment. Apportionment. And that's how do we assign representatives to a population. So apportionment. Apportionment is the process by which a finite number of representatives, is most equitably distributed amongst a given population. So is most equitably distributed amongst a population. Okay, so there are different methods of apportionment that we're going to cover here. So methods of apportionment. And they are all people's names. So the first one is Hamilton's method. Pardon me. Hamilton's method. The second one is going to be Jefferson's method. The third method is called Webster's. The Webster's method. The fourth method is called Huntington Hill. So two people, Huntington Hill method. And finally, the fifth method we'll cover in this section is Lowndes' method. Lowndes' method. Okay, so these are what we're going to cover in this section. It's going to be a real long section, so I might need to cut this into at least 2 videos. So let's recall that if I have a divisor into a dividend, what I get is, let me move this down a line. What I get is a quotient and a remainder. So basically, little d is called the divisor. Capital D is called the dividend. Q is called the quotient. And R is called the remainder. So for example, let's say I have a divisor of, what shall I use? Let's do 7 into a dividend of 33. So what do I get? How many times does 7 go into 33? Well, 7 times 4 is 28. So I'll have a 4. What I get is 28. And if I subtract that from the line above, so the difference between 28 and 33 is 5. So in this case, 7 is my divisor. 33 is my dividend. 4 is my quotient. And 5 is my remainder. Okay, so that's the terminology when we're doing long division. So hopefully everyone's seen that before, but let's note something just real quick. Note about this very problem. If I take and I divide 33 by 7, so let's have 33 divided by 7, because that's really what's going on here, 7 into 33. So what do we get? We get a quotient or whole number part of 4, and then a remainder of 5 out of 7. So there's 5/7 remaining. So that's what this means. A quotient is the whole number. 5/7, or 5, is the remainder out of divisor 7. And this is actually equal to, so 5 over 7 has a decimal expansion. So this will be 4 point, and 5/7 is actually 714,285 bar, meaning it repeats infinitely, those same numbers. Okay, so this is called our decimal remainder. Decimal remainder, as opposed to the remainder as seen in the long division problem. Once we actually take the remainder and divide it by the divisor, that's called the decimal remainder, this portion here. So the decimal remainder is 5 over 7. Not just the 5, but the 5 over 7, the whole quotient. Okay, so now let's start with Hamilton's method of apportionment. So Hamilton's method. Hamilton's method. So why did I bring up all that division stuff? Because clearly it's going to have something to do with what's going on here. So number 1, first we divide the population by the number of representatives. So divide the population by the number of representatives. Number of representatives. Okay, so this value is called the divisor. Okay, so once we divide the population by the number of representatives, we get a value called the divisor. So step 2, divide the population of each state by the divisor. So divide the population of each state, and this will make more sense once we actually do a problem. So the population of each state, by the divisor. So this value is called the quota. So this value is called the quota. Kind of like quotient, but we call it the quota for apportionment. So number 3. So allocate representatives. So once you find the quota, you allocate representatives representatives based on the quotient. Based on the, why did I say quotient? The quota, rather. The quota. That is the whole number part of the quota. That is the whole number part. Of the quota. Okay. And the last, if there's any remaining representatives, you allocate them as follows. So allocate any remaining representatives to those whose quotas have the highest decimal. So to those whose quotas have the highest decimal remainder. So have the highest decimal remainder. Okay, so let's actually see one of these problems in action. So here we go. So for example, so in 2010, the state of California had a population. So had a population, and here we go with big numbers. Population of, how much was a population? 37,253,956 people. So the state has 30 representatives. So the state has 30 representatives. In its House. So here's where we verge from reality. So let's assume the state has 3 districts. So assume the state has only 3 districts. So let's call them North, Central, and South. North, Central, and South. With populations. With respective populations. Of, let's see, for the North, let's do 3,777,400, comma, 11,614,237, comma, and for the South, let's do 21,862,319. So use Hamilton's method to allocate representatives. So use Hamilton's method. To allocate representatives. Okay, so the first thing we want to find is the divisor. So the divisor is what? We divide the population by the number of representatives. Okay, so the divisor will be equal to, let me actually move this up midway. It's going to be a quotient. So I divide the population. So what is the population of this state? It's 37,253,956. And I'm going to divide that by the number of representatives, and there are 30 representatives. I'll divide that by 30. So when I do put that into my calculator, I'm going to get 465,674.45. So that is my divisor. So now I need to think about the districts, the populations, and the quotas. Because how do I find the quota? So I divide the population of each state, in this case each district, by the divisor, and this is my quota. Okay, so let's create a chart here. So first I'm going to consider the district in the first district, then the population. Then for each of those we'll find the quota. Then we're going to find this mysterious number Q, which I'll get to in a moment. Okay, so how many districts do we have? We have the North District, we have the Central District, and then we have the South District in my fake setup here. Okay, so what was the population in the North? Let's see, what color shall I use? Maybe light green. So the population in the North was 3,777,400. The population in the center part was 11,614,237. And finally, the population in the southern part was 21,862,319. Okay, so now we want to find the quota. So let's start. What is the quota again? Well, the quota is the population of each state, in this case each district, divided by the divisor. So let's do an asterisk here for North. So for North, the population is 3,777,400, which I'm going to divide by the divisor. And we found the divisor to be 674.45. So what we get for this guy is 8.11165. So that's what I'll put here, 8.11165. Notice that I'm making the decimal as long as possible. Let's do the same thing for Central now. So Central had a population of 11,614,237, and I'm going to divide that by the divisor, which is 465,674.45. So what I get for the Central's quotient, or quota rather, why do I keep on saying quotient, is 24.94068. So 24.94068. Okay, now the last guy. Let's do this in red, I guess. So for South, our population is 21,862,319. And I will divide that by the divisor. 465,674.45. Okay, so what do we get? For the South, the quota will be, plugging this into our calculator, 46.9494765. Okay, so 46.94765. Okay, so based on this, the quota would be 8 representatives for the North, 24 representatives for Central California, and 46 representatives, so I'm just looking at the whole number here, for the South. Okay, but what is the total? The total in this case would be, well, if I add these up, let's see, 46 and 24 is 70, so that's 78. But I have how many representatives? Oh, why did I put 30? I wanted 80. Why is this making no sense? Let's make this 80 representatives. Yeah, 80. I just can't read my writing. No wonder. Please excuse me. Don't know what I'm saying. Do as I say, not as I do. Okay, so this makes better sense. So let's say we had 80 representatives. So that's why this number didn't make sense, because this was an 80. Okay. You're probably wondering, hey, the math didn't work, and you're right. Okay. 80. So the problem is I'm missing 2. So what I need to do now is look at the guys with the highest decimal. So I'm looking for the highest decimal remainder on my quotas. So if I have 2 more decimals, it looks like 9-4, and 9-4 is much larger than 1-1-1. So these 2 guys have the highest decimals. So I'm going to add 1 guy here and add 1 guy here. So now my totals will go to 8, 25, and 47. So once I do that, my total will be equals to 80, which is what I want. Okay, so had I not messed that up, hopefully you understand what I'm doing here. And sorry for confusing you earlier on. So now let's continue to Jefferson's method, which is similar to this. Hopefully I can read my writing this time. So Jefferson's method. Jefferson's method. Okay, so Jefferson's method is basically the same as Hamilton's method. So let me write that out. Jefferson's method. Method is the same as Hamilton's method, save for what we will get to, is the same as Hamilton's method until the very end. Same as Hamilton's method. So at least we'll be able to review it a little bit correct this time. Hamilton's method until the very end. The very end. So if after assigning representatives with respect to the quota, so if after assigning representatives. And let me be actually more thorough here. With respect to the quotient of the quota, with respect to the whole number, I'll write it that way, whole number of the quota, whole number of the quota. So, like up here, we did 8, 24, and 46. So I looked at the whole number of the quota first, and then we did the decimal. So, where am I? So if after assigning representatives with respect to the whole number of the quota, the result is as follows. So the result is we have now a list. Result is, so number 1, it's less than needed. So like we had above, less than needed. We had 78 when we needed 80. Then decrease the divisor. Then decrease the divisor. Remember, the divisor was the population divided by the number of representatives. In case number 2, maybe we have more than needed. So maybe, let's say we had 85 instead of 80 needed, then we increase the divisor. So then increase the divisor. So this is not a very good method here. Underline these, decrease or increase. This is a very poor method of apportionment, but I'll go through it anyways, so we can kind of review what we did. Actually, let me just say example above. So let's just go back to the example above. So example, using Jefferson's method in the example above. Jefferson's method in the example above. In the example above. So what I'm going to do, I'm just going to copy and paste this guy here. Copy. Paste. So we know what our divisor was, right? But note that we had, let me erase some of this. We ended up with too few, right? So too few. So in that case, we need to, it's less than, so we need to decrease. So decrease the divisor. So let's have the divisor, instead of being, less than needed, decrease the divisor. Yeah, okay. Just making sure I did this correctly. So I'm just going to go ahead and tack off all of those extra numbers. Let's just call the divisor 460,000. Even. Let's make it nice. A nice whole number that I can hopefully plug into my calculator. Okay, so let's see if I can do this correctly. So let's calculate the north. So what do we have in the north? 3,777,400. And now I'm going to divide it by the new divisor to get my quotient or quota. So 460,000, which is less than the original divisor. So what we get then is 8.211739. So that's what I get here. So 8.211739. We'll do the same thing for Central California, which has a population of 11,614,237. I'm going to divide that by my decreased divisor, 460,000. So what I get now for my quota for Central will be 25. Oh, interesting. 0.24834. So this is now 25.24834. And last but not least, for Southern California, we have a population of 21,862,319, which we're dividing by the decreased quote divisor of 460,000. And that gives us a new quota of 47.52678. Okay, so 47.52678. So now my quota Q, I just look at the whole number part. So we have 8, 25, and 47. And guess what? That does sum to, so the total, let me move this stuff down a bit. So the total is indeed 80 in this case, without having to redo anything. Okay, so now on to Webster's method, right? We've done Hamilton's, Jefferson's, now Webster's. So Webster's method okay, so proceed with finding the quota in Hamilton's method. So the quota, remember, is the population divided by the divisor. So proceed with finding the quota in Hamilton's method. The first method, right? Then, number 1, we round up or down. So round up or down based on the decimal. So based on decimal. So that is, if it's greater than or equal to 0.5, round up. And if it's strictly less than 0.5, round down. Okay, then step number 2. So if the values aren't consistent with the number of representatives, then we can use Jefferson. So if the numbers still don't add to the number of representatives, don't add up to the number of representatives, then use Jefferson's method. Okay. Let's see, do I have enough room? Let's see. Maybe I do. this up a bit. Okay, so for example, use Webster's method in the example above. Webster's method in above example. Okay, so in this case, I'm just going to use copy and paste. Hopefully it'll fit here. Yes, it will. Okay. Yep. Okay, so now for Webster's method, all we need to do is round up originally. So rounding up for Webster's, or sorry, this decimal is less than 0.5, so I round down here, round up here, and round up here. So what that gives us then for our quotas is, actually let me move this Q over a bit. So this is going to give us 8, 25, and 47, which we know adds to 80, so check mark. Okay, so that is Webster's method. Once again,